All right, so we are all very honored to have today Professor Chelsea Walton from Rice University. She is a distinguished professor in Rice University, and it's a true honor for us to have her here deliver these distinguished lectures in the series in Representation Theory in Mathematical Physics. Chelsea has a huge number of awards and honors that is very hard to list. So I'll just say quickly a few of those. I'll miss many of them. She's a Sloan Research Fellow. She's an AMS Fellow, a Humboldt Research Fellow in the German Foundation. She has an AMS Clayton Gilmore Fellowship Award. She was an NSF postdoctoral fellow at MIT. She was awarded the Lichnerovich Prize in Poisson geometry. She has a number of research and teaching distinguished awards from Rice University, the University affiliated at Urbana-Champaign. She just gave an ICM talk for a special meeting of the International World Women in Math. And only in the MS, she has, just for the MS, she has 3 invited addresses at various meetings. She wrote a textbook, first volume of a textbook on symmetries of algebras, which is just looking like that. The second volume is going to be coming very soon. And we have the privilege of hearing some material that she's going to be including in the second volume.
It's really generous of you. Thank you so much. Well, thank you all for coming to this lecture. It really is an honor to be here. I hope to keep these lectures really down to earth. I wrote them for people actually who are not in algebra. So if you have any questions, please stop me at any time. And I'm going to have the notes posted as well. Okay. All right. So I'm going to give a lecture series on Frobenius Algebras. These are some of my favorite structures in algebra. The reason why is because they're really old. And there are many characterizations of them. In fact, the first characterization goes back to 1903. So let's start there, start at the beginning. This is 1903. I really like reading papers from that, but I feel like they read like novels. Okay, so this is due to F.G. Frobenius. Okay, and here are his birth and passing date. And basically the goal is very basic, is to understand finite dimensional algebras. And let's stick with C algebras. And we want to do this using matrices. Because that's all they had back then in terms of algebra, just matrices. All right, so just to note, the term algebra actually didn't exist back then. They used to call these like hyper complex numbers. If you were to look at these papers. All right, so in order to start this game, we need to describe what an algebra is. It's basically the combination of a vector space and a unit ring. So let's fix a C basis. V1 through Vn of A. Here, so that's a vector space structure. And in order to understand ring structure, what we're going to do is pick up structure constants from the multiplication. So for any element A and A, what we're going to do is collect scalars. I'm going to call them beta ij attached to A and gamma ij attached to A. These are scalars. So that when I multiply Bi by A, I can write that in terms of the VJs like so, with these betas. Here, 5. And when I left multiply VJ by A, I can write them in terms of the basis elements like so. The I actually. Okay. All right, and the next part of the game is that we're going to package these scalars into basically linear maps. So let's form some linear maps, which I'm going to call beta, which takes A and sends it to an n by n matrix. Basically, it sends the element A to this n by n matrix with the betas. And let's form another linear map, gamma, that's defined in a very similar way, since A to the matrix formed by the gammas. Okay, so now the main question, others. The main question is basically written in terms of 1903 language. When does there exist an invertible matrix P? So it's in GL and C, such that when I take P and I let multiply by beta P, the same thing is taking P and right multiplying by gamma P. And this is going to hold for all A and A. All A and A. Now, the reason why we're actually interested in this question is because when this holds, this gives A a lot of symmetry, this gives a lot of structure to our finite dimensional algebra. And in fact, Frobenius noticed that this always happens for finite group algebras. So he was basically wondering, okay, what other finite dimensional algebras are there out there that have the same type of symmetry as a finite group algebra? Now, you might recognize this question in modern language here. We realize this as sort of like the, I'm going to define this more precisely in a minute, but here's as like the left rep of A, and this is kind of like a right rep of A. Basically, what we're asking is, when are these two representations equivalent? But back in 1903, we didn't have the word representation or module or anything like that. We didn't have computing. So that's a bad question. All we had was linear algebra. That's it. So that's what we're going to do. We're going to use the tools for linear algebra to address this question. All right. Are there any questions so far? Questions? Okay. Now, how do you think we're going to answer the question? Via what? Matrices. That's all we have. Matrices. Towards an answer. Towards an answer. What we're going to do is pick up some more structure constants for multiplication. So let's collect some scalars. M-I-J-K that comes from multiplying basic elements together. So these structure constants come from multiplying the basic element BI, BJ, now we come over K, M-I-J-K, BJ here. And these structure constants are going to help us answer this question in the following way. Basically, what we do is we form this thing called the parastrophic matrix. And I have a curiosity, has anybody heard of this?
What kind of matrix?
Parastrophic matrix.
Parastrophe.
Parastrophic. Okay, good. Already learned something new. Okay, okay. So let's collect a duple scalars, lambda. Lambda 1 through lambda n. This is an intuple scalars in C. Okay. Now the parastrophic matrix of A, we say at this tuple scalars here, this is defined to be the matrix given like so. What I do is I take the sum running over all K, lambda K, MIJK. So this linear combination of these MIJKs. So this is an n by n matrix, of course. Now, what's cool is that the answer to this question is yes, precisely when there exists a tuple of scalars, so that this matrix is actually invertible. Very concrete question is a very, very concrete answer. And in fact, this is the first definition of what's the definition. A finite dimensional C algebra A is Frobenius
if there exists a tuple of scalars so that its parastrophic matrix is invertible. Okay, so if you've seen a Frobenius algebra before, I guarantee you this is not the first version, not the first version. Now, of course, Frobenius back in 1903, he didn't just name the thing after himself, he owned some property. Later on, actually, folks who got involved in the 1930s, when they examined this property, they originally called these Frobeniusian algebras. And this long word, the 6-syllable word, actually made it into 3 papers. But then later, I guess a bunch of people were complaining, they cut it down to just that. But in any case, that's the first iteration of what a Frobenius algebra is. Let's do an example. Very concrete example. Let's take a 5-dimensional algebra formed by taking the polynomial ring in one variable, and let's quotient out by x squared. So it's a 2-dimensional C algebra. 2-dimensional C algebra. And let's just run this whole game. What is the C vector space? Well, we're going to take to be generated by the unit F, A, and the variable x here. And then that takes care of the vector space structure. And I'm going to be super basic on purpose and write down the multiplication table. Naughty, I know we're not supposed to be doing that. We're too grown for that, but I'm going to do it. I'm going to do it. And of course, we get 1x, x, 0 for the multiplication table. And now what we need to do is actually collect these structure constants that are formed by multiplying basis elements together. So here, what you get is that when you take 1 times 1, that's equal to 1. So this superscript is equal to 1, and everything else is equal to 0. So if I have 1, anything else is equal to 0. And if I have m1x with the x, I get 1, and likewise I get x mx1 with the x on top is equal to 1, and everything else is 0. Okay, so that takes care of these constants. And then now, if you were to pick off a tuple of scalars, 1 for each basis element, so for scalars lambda 1, lambda x, for C, what we end up getting is that the parastrophic matrix looks like so. I have a lambda 1, lambda x, and 0. And is this thing invertible for some choice of lambda 1 and lambda x? Is it ever invertible? What do you think? Can this thing ever be invertible? No, I'm asking you something basic. Yeah, it can be. Yeah, what do you have to do? What do you have to do? You just have to take lambda x to not 0. So this is invertible. Or lambda x not equal to 0. So what we end up getting is that this algebra here is Frobenius. It's a very elementary way of checking if an algebra is Frobenius. And of course, this works best when your algebra has small dimension. Now, here's another example. If you are bored later, show that this 3-dimensional algebra formed by taking the polynomial ring in 2 variables, polynomial ring, so these variables commute, quotient out by x squared, xy, and y squared, show that this is not Frobenius. Not Frobenius. Okay, you just run this same game. Okay. All right, and then this game died for about 3 decades. So before I move on to the 1930s, are there any questions?
What did Frobenius wanted to do with this? What was his motivation?
To find more algebras like finite group algebras.
Ah.
Yeah. He was doing rep theory before rep theory was invented, yeah. Yeah. Any other questions? Okay. Let's fast forward to the 1930s. All right. Hey. Ooh, what for this? The other rebates are rules based. The other one was this one? Oh, yeah, that juice, okay. Thank you for telling me now, as opposed to like 45 minutes in. Shaves 2 minutes off my time. Okay, so now, let's fast forward to 1930s. Woo, that's not good. Okay. So, the reason why Frobenius algebras emerged again in the 1930s is because abstract algebra was developed. Now, we know what a ring is, and an algebra, and a module, and we know if it did everything. I give her all the credit for inventing abstract algebra. So now that you have these tools from abstract algebra, we can look at these types of finite dimensional algebras in an abstract way and give them numerous characterizations. So, let's do it. Actually, I'm going to drop that here. There's a theorem, very important theorem, and this is due to Browers, Nesbitt, independently Nakayama, the three that gave the original term Frobeniusian, in a series of papers ranging from 1937 to 1942. And what they showed is that if you take a finite dimensional algebra, the algebra, okay, you have that the following are equivalent. First of all, one, you have the A is Frobenius, that's what we're after. And by A being Frobenius, I mean that the parastrophic matrix attached to it, some parastrophic matrix, is invertible. Okay. A second characterization is given in terms of rep theory. So if I form two representations of our algebra, now instead of having a matrix algebras here, I'm going to use endomorphism algebras. So I'm going to go from A to endomorphism from A, like so. And we can send A to the map that's given by left multiplication by A. So B equals A. This is called the left representation of A, left regular of A. A acts on A. And we can also form another representation of A, but now we're going to use the dual, the vector space dual of A, so A. Combine like so. So now I send A to the map that sends a linear functional F to a linear functional defined like so. This is given by right multiplication. Right multiplication. So, this goes to be A. Okay, so this is called the right regular map. Right regular map. Okay, and what you want is that these two representations of A are equivalent. Okay, so that's the second characterization. The third one, well, if you like representations, you like modules. So this one, you have a isomorphism of right A modules. Let's call it 5, going from A to A dual here. And here you have that, so here, A acts on B by just multiplication. And here, A acts on a linear functional just as this type of evaluation. So you have that these two are right A modules like so. Okay, so we have matrices, representations, modules. Fourth one, it's very algebraic. There's going to be a C linear map which I'm gonna call mu. It's a form on A, so that the kernel of this map doesn't contain any right ideal of A. So that the kernel of this map has no non-zero right ideal of A. No non-zero things, no non-zero right ideal of A. This is often called a Frobenius form. Frobenius form. This is probably the most popular characterization. Here's another one. Here's another one that I think, for me, it's the most fun to work with. This one, you're going to have a pairing on A that is non-degenerate and associative. So you have a non-degenerate, associative, linear map called P, going from 2 copies of A to C. Okay, so sometimes this is called a Frobenius pairing, and it comes equipped with a co-pairing going in the other direction. So those are 4 different characterizations of what a Frobenius algebra is. I can keep going, like there are tons of others.
Sorry, in point 5, do you assume that P is symmetric or something like that?
P is symmetric?
Yes.
No,
Not necessarily.
not just non-degenerate and associative. But if it's symmetric, then we get what's called a symmetric Frobenius algebra, which is a special, which we're going to see in lecture 4, actually.
Ah.
Yeah. Any other questions? But these properties are symmetric, so I can replace this with left modules. It's equivalent. I can replace this with left ideals, and it's equivalent. Well, you already have left and right up here, but in any case, all these are equivalent. Now, how does this proof work? Well, 1 equivalent to 2, basically this parastrophic matrix gives us the equivalence. This gives us the equivalence. So this parastrophic matrix, this is the matrix of the equivalence of these representations. Right? 2 being equivalent to 3, if you know how to translate between representations and modules, basically these conditions translate the same way. So this follows from how you go back and forth between reps and modules. Okay, so basically we're just like repackaging the information 1, 2, 3. Now here's where it gets a little bit more interesting. 3 implies 4. If I start off with an isomorphism of modules and I want to cook up a Frobenius form, well, what I do is I just define my Frobenius form to be phi at 1. So I send 1 to a linear functional, and that's going to satisfy this property. 4 implies 5. Okay, if I start off with a Frobenius form and I want a P, how do I define the P? What I do is I take my 2 copies of A, I first multiply, I land in 1 copy of A, and then I hit it with the form. And it's going to end up being non-degenerate and associative. And then lastly, 5 implies 3. Well, if I start with a non-degenerate associative, if I start with a Frobenius pairing, how do I get this isomorphism of modules? Basically, I define this isomorphism like so. I send an element A to this linear functional P blank tensor A. That does the trick. Are there any questions on this theorem? Now, what's cool about this characterization is that you can start to understand the Frobenius condition through a bunch of different lenses. And what that enables you to do, or enables us to do, is to come up with a bunch of different classes of examples. And sometimes it's easier to see in a big finite-dimensional algebras Frobenius by using, let's say, characterization 3/4, for instance. So here's some examples. All right, so As I mentioned before, this is Frobenius's original notion, original, I guess, prototype, finite dimensional group algebras. These are Frobenius, and you can see this either by 1, 2, or 3 in a nice way. So it's a nice class of examples. Another class of examples of Frobenius algebras that are probably a lot of people's favorite are matrix algebras. Matrix algebras. These are Frobenius. And the way to see that these are Frobenius, the best way actually, is to use characterization 4. Characterization 4, because here, if you use 4, this Frobenius form, it's just going to be the trace map. Just the trace map. The map just sends a matrix to the sum of the diagonal matrix, sum of the diagonal entries. So matrices are Frobenius. And I guess a spicier example are various cohomology algebras. Various cohomology algebras. And here, let's take X to be nice and controllable. So it's some finite dimensional compact oriented entity. And this just trains of using characterization 5 through Humphrey and Walton. Okay. All right, so lots and lots and lots of families of Frobenius algebras working about. You have worked with them whether you realize it or not. Okay, any questions? Okay, so let's hold on to.
Here, in the example of homologies, for triangle is symmetric, so it's going to be a symmetric Frobenius algebra,
A
right?
little bit more, yeah, a little bit more, yeah. Every time I give these talks, there's always one person in the audience that's like, I like symmetric, tell me everything, tell me everything about symmetric. Yeah. Which is cool. Okay, let's keep a hold of these matrix algebras here. Now, once you have a nice condition, it's nice when it's actually preserved under operations. It's nice when it's actually preserved under operations. As a fact, you get that if you take the finite direct product of a bunch of Frobenius algebras, it ends up being Frobenius. Okay, so these two facts together actually give us that finite dimensional, semi-simple C algebras are Frobenius. And the reason why is because it's due to a very, very probably the most important theorem of non-commutative algebra, the Artin-Benenberg theorem. What it says is that if you have a finite dimensional semi-simple algebra, it's isomorphic to a direct product of matrix algebras. So finite dimensional semi-simple algebras, a nice class of algebras are Frobenius. Now, since we're working over C, this is also the same thing as finite dimensional separable algebras, if you like to remember these. All right, so I defined what a Frobenius algebra is. I gave a bunch of characterizations. I gave some examples. Clearly they have ties to other fields, but I wanted to see like how prevalent these structures are. So I did a Google search. Bear with me. I have to draw a bar graph. I'm sorry. Yeah, I'm gonna draw a bar graph on the board. So let's check out popularity throughout the years. Popularity throughout the years. So what I did was basically, I went on Google Scholar and I counted the number of hits I got for the term Frobenius algebra in 5-year intervals. Okay, and I did this, let's say, starting in 1950, 50. Okay, and it kind of scaled up, so we have 200, 4, 6, we have 8, and then we have 1,000, definitely not that much in 1950, and then 1,200, and then I just did it in 5-year intervals, so this is 64, 74, 84, 94, 2004, 2014, this is a really crude bar graph. So starting in the 1950s, all the way up to about 1989, maybe there were like 30 or 40 hits. It wasn't like, didn't grow too much. I mean, the abstract theory kept being developed, but it didn't really, it was like that basically. And then around 94, something happened. It kind of like jumped a bit. And then it jumped again. Like here, in 2004, and then it's maybe about here. And then it just kept going. Kept going.
I think it was in 1994, this Frobenius manifolds were introduced. Maybe this is one of the reasons why.
One of the reasons why.
Probably.
One of the reasons why. Now, naively, when I saw this, I thought, oh, the internet was so bad. So as soon as everybody got, Internet Explorer at home, they would put the term Frobenius algebra. It's the first thing they did, they wrote a paper on it. But that's not true, that's not true. There's something else that happened here. And just as a control, I did this for the term separable, because I knew separable was less popular than Frobenius algebra, even though it's a subclass, a very important subclass. And it kind of looks like this. I mean, less popular, less popular, less popular. 70s, they actually were more popular, and less popular, and then it just stagnant. So there's something that happened here. Something happened here. Something happened
Conjecture of happened there.
here. Okay.
In 1992 or 1994, I don't remember the precise year, Frobenius manifolds.
I do, yeah.
Exactly.
I'm going to tell you another reason. But that is one reason. To explain what happened, I need to tell you some more stuff. Okay. What I need to do is basically move into the world of modular categories. Okay. So in order to explain what happened, what I need to do is tell you, basically move to the monoidal setting. And we're going to do this in lecture 2. I'm going to tell you what a monoidal category is from scratch. And then what I need to do is describe what algebraic structures are in these categories. Algebraic structures in monoidal categories, including Frobenius algebras. And that's going to be done in lecture 3. I'm even going to show you how to do computations and all this sort of stuff, in case you want to do some stuff later. And then what I'm going to do is make ties to these things called topological possibilities, and that is really neat things to take off. So we're going to make ties to topological quantum field theories. I'll explain what they are very quickly. This is going to be done in lecture 4. Lecture 4. And then to finish things off, I'm going to basically talk about Frobenius structures. Once you have Frobenius algebras, you can build other types of Frobenius structures that I think are quite interesting out in there. That's going to be lecture 5. Right, so that is the outline of the talk series. So this is going to be based on some books that I'm writing. They're called Centuries of Algebras. This one's already out. This is volume 1. This is basically like algebras over a field, categories, monoidal categories, and algebras in them. Pass it around. But this is my proof, which means it has all sorts of scribbles in it. And then This is volume 2 in progress, clearly, because it's in a kitty binder. This is about basically these things called coalgebras, which I described in lecture 3, as well as Frobenius algebras, both over field and different.
There is also Frobenius algebra. This.
Frobenius algebra is dual, so it's.
I'm asking.
Yeah, nobody knows. Yeah, if you're not interested. That's what I mean.
Oh.
Any questions? Okay. All right, in the last few minutes, although, well, I was totally fine through this actually. I take off at 50 minutes, it just comes from teaching. So what I want to do is basically expand the setting of Frobenius algebras because we talked about subclass of Frobenius algebras. And what I want to do is describe a nice class of generalizations of Frobenius algebras because there are actually lots of open questions in that setting that I have no idea how they can. So it's worth having this on the radar. Especially if you like finite dimensional algebras. Oh, so this is hierarchy. I spell that. Hierarchy. Finite dimensional C algebras. Okay, we have Frobenius algebras. They're finite dimensional. Okay. Finite dimensional. Okay, and we show that semi-simple algebras, or in this case, are equivalent to separable algebras. They're a nice subclass. And if you wanted an algebra that distinguishes these two, you could just take the algebra that we looked at before, this two-dimensional algebra CX mod x squared. It's Frobenius, but it's not semi-simple. The concepts that I really want to highlight now that I think are really interesting are these things called self-injective algebras. And they end up being equivalent in the finite dimensional case to these things called quasi-Frobenius algebras. And again, I'm highlighting this because I think there's a lot of open questions for this class, particularly in the media context that we talk about. Okay. So I'm going to give you the definitions, I'm going to give you examples, I'm going to give you the white hair when Frobenius. And now in lecture 1. Questions?
Can you say that this example, this simple example, is a Grassmann variable? In physics, we call this Grassmann variable.
Yeah. Yeah.
Then, but you have classification of some semi-simple superalgebras. And then what will happen with this areas?
I don't know what semi-simple superalgebra is.
Yeah.
But if I look at the generative
Just
relation.
where to fit this in that picture.
Yeah, I mean,
That's
semi-simple Frobenius, super has something to do with Z2. It's Frobenius, and if you have an operation that combines the two, reserves Frobenius, which more likely it does, it would have to be Frobenius as well. It's just my guess. Okay. All right, so I want to describe this classified dimensional algebras. Give me a try here. Okay, so this is pretty easy to describe. If you know homological algebra a little bit, C algebra, whether it's finite dimensional or not, it is self-injective. It is self-injective. If the regular module is injective. If the regular module is injective. And you can just take as a fact, and this is sort of a symmetric condition, you can use the right regular module as well for this condition. In the finite dimensional case. Right. So that one is not so bad. Now we need to describe these things called quasi-Frobenius algebras.
Sorry for interrupting. What happens if you take the left module? Doesn't work.
Oh, I take the left module here.
No. There, said.
This is right.
Yes, but that doesn't work with the left module.
Yeah, by definition.
Okay.
Yeah.
Okay. Sorry.
Okay. Now, what is this quasi-Frobenius condition? It's a lot more concrete to work with. Basically, what we want to do is take A and decompose it in a very, very nice way, so that its dual has the same type of decomposition. Has the same type of decomposition. So now I'm going to take a finite dimensional algebra. I have to give you a bunch of words, I'm sorry, especially for folks who do finite dimensional algebras. You know all these words already. But let's set E and E1 through En. Anytime I write down an E, it's going to be an idempotent element. Idempotent element today, so they square to themselves. We say that E, I, EJ are orthogonal. If EI, EJ is equal to EJ, EI is equal to the Kronecker delta of the EI. We say that idempotent and non-zero idempotent is primitive. Primitive. If you can't break down this idempotent anymore by using orthogonal idempotents, and the reason why you care really is because if you take the cyclic module generated by this primitive idempotent, it ends up being indecomposable. So it's a nice building block for the module theory of A. That's why you care about these things. Gives you a nice indecomposable piece of A. Next bit, what we want to do is take the unit and write it as a sum of nice idempotents. So we say that these idempotents are complete if they're pairwise orthogonal. And primitive. Okay, and you can write the unit as a sum of such idempotents. Okay, and we say that they're basic. Say that this collection of idempotents are basic if they're pairwise orthogonal and primitive, and you don't have any repeat indecomposable factors. So basically, once you have a complete set of idempotents, you can always cut it down to something basic just by throwing out the repeats. So you can get this by cutting down. And basically, the whole point of this is that you can always write your algebra A like so. You can write it as a direct sum of factors that look like so, as a right A module. This is the canonical decomposition of A. The canonical decomposition of A. And in fact, A is basic if all these superscripts are equal to 1. All right. So again, the whole point of this is that we're using idempotents to break up our algebra. We're using idempotents to break up our algebra into indecomposables. So if you have any finite dimensional algebra, you can write your regular module like so. Now, what is a quasi-Frobenius algebra? So, let's take this setup. Let's take this setup star. So given star, we say that A is quasi-Frobenius. A is quasi-Frobenius if we also have that the dual of A, can be broken up like so. The sum of these nice indecomposable right A modules, but not the same number of copies. These superscripts S's can be different than the R's. Right, so that is what a quasi-Frobenius algebra is. And these two, they look very different than one another. They look very different than one another. But I would say this is like homologically nice, and this is concretely nice. And what's amazing is that what you get is that these two are actually right. I put a sketch of the proof of how this book works in the notes, but I'll skip it. I'll skip it here. Any questions on this?
All right, what's the last comment? E.
Hmm?
So what's the red down?
Yes.
Ah.
If you get that these two are from. So I told you that these are generalizations of Frobenius algebra. So I should show you why Frobenius algebra applies to this. And maybe when you actually, if you impose a certain addition on in this bubble, how you would get back to this bubble. So now versus Frobenius. How did these notions actually compare with being Frobenius? First of all, Frobenius actually implies self-injective or quasi-Frobenius. Let's see why that's true. Okay, so if A is Frobenius, we have that A is isomorphic to its dual as in right A module. That's one of those characterizations we discussed. A is isomorphic to its dual as a right A module. All right, and well, that's going to give us quasi-Frobenius. And that's going to give us quasi-Frobenius, so it gives us self-injective. Now, so I show that basically this bubble lies inside of this bubble. What's cool is that if we have self-injective, this is, by the way, A is always bidimensional. If we have self-injective / quasi-Frobenius plus basic, then we get Frobenius. So if I were to sneak in and say basic here, I go from this bubble after this one. See why that's true. If A is a basic algebra, then we know that its decomposition looks like so. I have that it's basically E1A plus some EMA, where these don't repeat as a right A module. Okay. Now, that's basic. This whole self-injective quasi-Frobenius condition, particularly the quasi-Frobenius condition, tells us that now a dual has a similar decomposition. I could write the dual of A with the same factors, but I might have multiplicities, say with T's. Okay. Quasi-Frobenius gives me this. But I have that the dimension the dimension of A, which is finite dimensional, is equal to the dimension of its dual. The dimension of these two vector spaces are equal, therefore all these t's have to be equal to 1. And that gives us now that A is isomorphic to A dual as the right A module, which implies Frobenius.
How do we know that they're greater or equal than 1?
Oh, that's part of it. That's part of this. Yeah.
Mhm.
Any other questions? Okay, so we have Frobenius. We have a nice subclass of several or semicircle algebra, and we have a nice superclass, if you will, of algebras that generalize Frobenius. And we know how to not go back from one class to another. Now let me just end with some nice examples that helps distinguish these classes. Let's see pictures. Pictures. Let me give you my favorite Frobenius algebra. I mentioned that a lot of people like matrix algebras as their favorite, but I like this one four-dimensional one as my favorite. Many examples. And this actually appeared in a paper of Nakayama going back to 1939. Again, reading these old papers from the 1930s, you can pull some good stuff out. Okay, so let's keep going back to these same things. Let's take this algebra, which I'll call T. And instead of like using a quotient of a polynomial ring, I'm going to use a quotient of what's called a path algebra. So what I do is I take a directed graph that has some vertices and arrows. And what this algebra is basically the vector space are all the paths of this graph, and all the relations are determined by composition, essentially. So this is the graph I'm going to use. And the path algebra is just a linear combination of paths. But I need it to be finite dimensional, so I'm going to force the path AB to be 0, and also the path BA to be 0. And you compute this thing is actually 4-dimensional, and it's Frobenius. Right? Very nice example of a Frobenius algebra. Let's take this example and kick it up a notch. I'm going to take this direct graph, which is often called a quiver. I'm going to expand it a bit. Basically, let's take a copy of this quiver here. So I have 1, 2. I'm going to go path A, path B, and I'm going to take a copy of 1 down here. Path A prime, path B prime. And I'm actually going to connect these two with a path C and a path D. Lots of paths. Now, the algebra is going to be formed by taking in copies of B. So I'm going to kill all of these 2 cycles, AB, BA, A prime, B prime, B prime, A prime, as well as A, B prime, and A prime, B. And I'm going to force the path CD to be a vertex, E1 namely, DC to be the vertex E1 prime. And then I'm going to force 2 cycles basically to collapse to arrows. So CA prime is equal to A, DA is equal to B prime, BC is equal to B prime, and B prime D is equal to B. All right, that's a mouthful. But basically, I forced all of my 2 cycles to either be arrows or vertices in a nice way. This thing is 9-dimensional. It's actually not terrible. And it is not Frobenius. And it is self-injective. Quasi-Frobenius. And here's the killer. These 2 algebras are actually really equivalent. So you actually end up getting that these 2 algebras have the same representation here. They have the same module theory, they have the same representation theory, even though they have different features. So what we end up getting over here is that this property of being semi-simple, severable, this is Morita invariant. If you have two algebras in a Morita equivalent, both of them are either simultaneously semi-simple or not. This whole Frobenius thing, this nice thing that I've been describing this whole time, this is not Morita invariant. This is not Morita invariant. Because I have two algebras that have the same representation theory, but one's Frobenius and one's not. But amazingly, when you go up here, you pick up Morita invariant. So that's one reason why perhaps you should care about expanding your world beyond Frobenius algebras. Okay, that's all I wanted to say for lecture one. Thank you very much for listening.
Any questions?
Yes, this one might be too simple, so I apologize in advance. Can we actually define Frobenius algebras over a general commutative ring?
Yeah.
So if we don't require the ring to be filled.
Yeah, so like, you're gonna see one of the little categories tomorrow. And you can define Frobenius algebras in one of those categories. So once you get in that framework, you can define Frobenius algebras everywhere. Yeah. Yeah.
Other questions? I was wondering where do Hopf algebras fit in this picture?
Yeah, so finite dimensional algebras are always Frobenius, but you have to change the structure of the Hopf algebra. So, yeah, they're related because these are both structures that have a multiplication, a way of merging, and a co-multiplication, a way of breaking, which you're going to see later. But the compatibility between those operations are different. But you happen to have that finite dimensional Hopf gives us Frobenius.
So we'll see this a little bit later, or
I think of it, yeah, that's actually volume 3.
Yeah.
The books of Hopf algebras. Yeah, I'm leaving, because once I open up Hopf, that's like another 5 lectures.
That's one of the characteristics they have for announcement of to be for use and the executive could say exact this.
Oh. That happens, yeah. So that happens at this level here, and actually that's, I can point you to the exact result, actually. Yeah.
Yeah,
So you want like a Frobenius category.
yeah, I wanted to ask, this part of objective equation exactly, I don't think it was, did the Frobenius, think about this factor or it come much later?
Much later, Frobenius wasn't around when modules were. No, but, yeah, homological algebra was really developed in the 50s. Yeah. But that fact is in my.
and the big development about Frobenius algebras was right after the Great Depression.
It created what?
The big developments on Frobenius algebras were right after the Great Depression. Before
Yeah,
World War
well,
I.
you know, you need something to make you
Time
happy.
period.
The nice instructions, I guess.
Any other questions?
Maybe you will mention in the future lectures. There also is a definition, current definition use the algebra structure and co-algebra structure.
Yeah, that's actually after I do minority stuff, and I'll draw the pictures and everything.
Yes.
It's funny how, like, nowadays when people learn Frobenius algebras, they learn the 90s definition first, the one that you're mentioning, and then nobody's ever heard of the 1903. So, promoting very, very old school stuff. It's important.
Any other questions? Thank you, Chelsea, for the wonderful lecture.